In this video, we will be looking at the composition of functions or composite functions. A composite function is just when you have a function that goes inside another function. And the notation we use is f of g of x in this format, or f at g of x using this function notation that's showing the inside function is g of x and the outside function is f. And when you have a composition like this, f of g, the inside function is g of x. So the y values, or the range of g, becomes the domain of x. And let me show you what I mean by that with this mapping diagram. So on the left side, I have the x values 1, 2, 3. And this notation of f of g of x, just using my function notation knowledge, I need to figure out what g of x is equal to first, and then I can put that value in for f. Well, g of x is equal to 3x squared. So I'm going to take each of the x values and put them into 3x squared. So when x is 1, 1 squared is 1 times 3 is 3. When x is 2, 2 squared is 4, and 4 times 3 is 12. When x equals 3, 3 squared is 9, and 9 times 3 is 27. So these are the y values, or the range, of g of x. Now, my function notation tells me I'm taking f of g of x. So all of these values are getting plugged into f at x. And what is f at x? 2 times x. So I'm going to take each of these values and just double them, because these y values of g become the x values of f. So 2 times 3 is 6. 12 times 2 is 24. 27 times 2 is 54. So what did I actually do? When we did f of g of x, again, using my regular knowledge of function notation, I'm taking f at g of x, and g of x is 3x squared. And this function notation tells me replace x in f at x with 3x squared. So instead of 2x, I'd be writing 2 times 3x squared, which is 6x squared. And that's what this mapping diagram spits out. So I was given, again, to recap, I was given x values. I had to put them into g of x to spit out its y values, and these g of x was plugged into f at x to get these final coordinates. So let's look at a few examples where we're practicing this notation and identifying the values for these composite functions. So in our first example, we're given function f and we're given function g with a set of coordinates. And the first question asks us to find f at g at 3. Well, the first thing I need to do is figure out what g at 3 is. G at 3 is saying when x is 3, what is y in function g? So I go looking, and here's the coordinate. When x is 3, y is 7. So now I can replace g at 3 with 7, because that's its value. And now I'm being asked to find f at 7. In function f, when x is 7, what is y? Here's the coordinate. Y is 4. Let's try another one. G at f at 9. So again, I'm working inside first. F at 9. In function f, when x is 9, what is y? Y is 3. So I'm evaluating or looking for g at 3. So when x is 3 in function g, what is y? It's this coordinate again. Y is 7. So that's us reading these coordinates with this composite function notation. In the next example, we're given equations instead of the coordinates right away. So first, we need to find f at g at 1. And if you don't like this notation, it is the same thing as f at g at 1. So we need to figure out what g at 1 is, and then we can sub that into function f. So I'm going to write this in 2 steps. On the side here, I'm going to figure out what g at 1 is. And g at 1, I look at g of x, it's 2 times x. Well, 2 times 1 is 2. So I'm evaluating f at 2, because that's what g at 1 is. And f at 2, I'm going to function f and replacing x with 2. So instead of x squared, I have 2 squared and then minus 3. That's 4 minus 3, which is 1. For the next one, we're looking for g at f at 1. In the previous example, I did this in 2 steps, but we could also work inside with one function notation. So I'll leave the g on the outside. F at 1 means replace x with 1 in function f. So that would be 1 squared minus 3. 1 squared is 1, minus 3 is negative 2. So now I can do g at negative 2. Well, function g just tells me to take 2 and multiply it by the x. So 2 times negative 2 is negative 4. And you can show your work however you'd like. You can do it in 2 steps like I did in A, or you can do it all in one go like I did in B. Next, f of g at 3k. So we're not actually solving for a value here. We're just cleaning up an expression. So this is f at g at 3k. So we're working from the inside out. We need to start with g at 3k. So that means I'm going to do 2, and instead of x, I'm going to put 3k. So that's f at 6k. Now I can go into function f and replace x in there with this new 6k. So I'll write 6k all squared minus 3. And when I apply the exponent of 2, that's going to be 36k squared, subtract 3. Okay. Another one. F at g of x. Well, again, working from the inside out, g of x is 2x, so I'm actually trying to simplify f at 2x. So instead of x squared, I'll do 2x all squared, subtract 3, and that's going to give us 4x squared, subtract 3. So this is a new function, a composite function, where one function was placed inside another. Okay, for E, we're going back to subbing in values. We want to find f at g at 3. This one I'll show with the little side calculation. The other one I'll do it all in one go, just again to see both versions. I'm going to do something on the side. I'll figure out what g at 3 is. So 2 times x, or 2 times 3, is 6. And that's what I'm going to replace g at 3 with. So what I'm actually trying to calculate is f at 6. So again, 6 squared, subtract 3. That's 36 minus 3, which is 33. Finally, g at negative 2. So I'm putting the same function inside itself. I'll first figure out the inside. So g at negative 2. Well, that's just doing 2 times negative 2, which is negative 4. So now I'm evaluating g at negative 4. So going back again into that g at x function, so 2 times x, but now I'm subbing in negative 4. And I get negative 8. So it's always working from the inside out. Our next example. Given f at x equals x squared minus 2x and g of x equals x plus 1, sketch the graph of f of g of x. Well, the first thing I'm going to do is try to create a new equation for f of g of x. Maybe it's going to be something familiar that we already know. So f of g of x means, working from the inside, g of x is just x plus 1. So I need to put x plus 1 into all of the x's in function f. I'm taking one function and putting it inside another. So function f is x squared, so I'm going to do x plus 1 squared minus 2x, so minus 2 times x plus 1. And now I'm going to clean this up and see what happens. Now please be careful here. X plus 1 squared, write your bracket out twice. For the negative 2 times x plus 1, I'm just distributing that in. And now I'll do my distributive property. So x times x times 1, 1 times x, 1 times 1, and then the rest. And now I can collect my like terms. The x's cancel out because we have 2x minus 2x, and then 1 minus 2 is negative 1. So this composite function, f of g of x, is just another parabola, and luckily this is in vertex form, so it's the basic parabola that has been shifted down 1. So the vertex is 0, negative 1, and this parabola hasn't been stretched or compressed or reflected in any way. So it's that same step pattern from grade 10. So a step of 1, a step of 3, step of 5, or whatever strategy you want to use to graph this. And here's f at g of x. Okay, next example. The circumference of a circle is a function of its radius, r. So let's write a little equation for that. Well, we know what circumference is. Circumference is 2 pi r. Express the circumference as a function of the diameter. Well, we know that the diameter is equal to 2r. And if that's true, and I look at my original circumference, I see 2r here. So their circumference can also be written as pi d. So you can actually think of the first circumference formula I wrote as a composite function, where I'm putting the diameter equation inside the circumference equation. The volume of a cylinder is a function of its radius and its height. Okay, so the volume of a cylinder is pi r squared times height. So there's your radius and height. Express the volume as a function of the diameter and the height. Okay, well, I don't see 2r like I saw nicely in the previous example, but I do know that the radius is equal to the diameter divided by 2 if I just rearrange this diameter equation, so I can put that in. So I'm putting a new function inside. And now I can just clean this up. So pi times diameter squared times height all over 4. So there's applying those composite functions for something like formulas related to geometry. Okay, next we're going to do some domain and range related to these composite functions. So we have f at x as the rational function, and we know rational functions, restrictions come from the denominator. Then we have g of x, which is linear. Nothing crazy with the domain and range there. It's just xcr and yr. H of x is the square root function, square root of x plus 5, and we know restrictions come from the fact that you can't square root a negative. So we'll take all of that into consideration when we do our composite functions. So the first one is f of g. So f of g of x. That means we're taking the inside function, which is the linear, 2x plus 1, and we're putting it into function f, which is the rational. So I'm going to replace the x in the denominator with 2x plus 1. And now I can think about this equation and do the domain and range. Now I know typically my domain comes from the denominator, the restriction there, because you can't divide by 0. Well, for this equation, my denominator is 2x plus 1. So if I were to set 2x plus 1 equal to 0, because I can't equal 0, and I isolate and divide by 2, I get x cannot equal negative a half. That's my domain. And then my range, we know that the rational functions also have horizontal asymptotes at y equals 0. And because I don't see any up-down movement here, we're going to have the same restriction. Or we could also look at it as the horizontal asymptote. And because the degree in the numerator is less than the degree in the denominator, the horizontal asymptote is at 0. So I'm not using any new skills to get my domain and range. I just have to get that composite function first and then go back to my prior knowledge. Next, we're going to do g of f at x. So my inside function is now f, which is the rational. And I'm going to put that rational into the x of the linear equation. So 2 times 1 over x plus 1. And then if I clean this up, that's 2 over x plus 1, but I would like a united fraction, so I'll get myself a common denominator. So 1 can be written as x over x, and then I have 2 plus x all over x. And now we can think a little bit about that domain and range in terms of rational functions. Well, my denominator is just x, so that means x can't equal 0. That's where you'd have that vertical asymptote. My range, well, if I look at the degree of the numerator and denominator, I see the degrees are the same. They both have x's. They're both linear. So I look at the leading coefficient. Now, the leading coefficient, remember, is the coefficient of the highest degree term, which is x. The coefficient here is 1, the coefficient here is 1, so we have a horizontal asymptote at 1, which means y cannot equal 1. All right, final one. We want f at h at x. And h of x, the inside function, is the square root of x plus 5. So let's see what that's going to be. We're taking that inside function and putting it into the rational. So 1 over the square root of x plus 5. Now again, I'm using my rational knowledge here. I know that I can't divide by 0. I also know I can't square root a negative number. So in order for me to be able to square root this value, x has to be greater than negative 5 or equal to negative 5. However, if it were equal to negative 5, I would end up with 0. And the square root of 0 is 0. And I can't divide by 0. So I actually can't be equal to negative 5. I just have to be greater than negative 5. So my domain, x is an element of all real numbers such that x is greater than negative 5. And I'm not going to be less than it because then I'm trying to square root a negative, which is not possible. And then finally, because of this restriction, the fact that I can't be less than negative 5, I'm not going to have multiple curves to this function like I normally would with a rational. So it's not just that I can't equal 0 for the horizontal asymptote, it's going to be that I have to be greater than 0. And you could also think of this logically. If I'm punching numbers into x here, and this is going to give me the square root of a positive number. The square root of a positive number is positive. So I'm going to be doing 1 divided by a positive number. That's going to give me a positive number. There's no way for me to get any negatives, and there's also no way for me to get 0, because there is no value I can divide 1 by to get 0. So that's it for my range. Y is greater than 0. All right. Given f at x equals the rational base function and g of x equals the base parabola, show that f at g of x is the same thing as g of f of x. Now, this isn't a very common thing to find, but sometimes the composite of one function is the same as the composite in the other direction. So let's just see what happens. Let's find f of g of x, which means replacing x with x squared. That's our inside function. The parabola is the inside. That's going to give me 1 over x squared. Let's look at the other way around. G of f at x. Well, the inside function is now 1 over x. So I'm going to take 1 over x and square it. Well, that also gives me 1 over x squared. So therefore, f of g is the same as g of f, or composite. F composite g is the same as g composite f. Next, if f at x is equal to 3x minus 1 and g of x is equal to x squared plus x plus 2, determine the values of x such that f at g of x equals g of f at x. So this is just saying there might be one or two x values that when I plug that value into function f and then plug that y into g, it's going to be the same thing as me plugging that x value into g and then taking that to plug it into f. So we need to find those perfect values that make that work. So f at g of x means f at x squared plus x plus 2. And then g of f at x means g at 3x minus 1. So I'm just rewriting this, but putting the inside functions in the bracket. Now I can see this has to replace this x value in function f. So that's going to be 3 times x squared plus x plus 2 minus 1 equals, and here this has to go in and replace all the x's in g. So that's going to be 3x minus 1 squared plus 3x minus 1 plus 2. I could put brackets here, but they really don't make a difference because the coefficient of x is just a positive 1. So I'm just not going to put them. And now I just have to do some cleanup. So distribute the 3 in. And then for 3x minus 1, remember, you are writing the bracket out twice and doing distribution. So that's going to be 9x squared minus 3x plus 1, and then I'll write the rest. And now collect your like terms. And when you collect them, and even before you collect them, you should see that this is a quadratic equation at this point. And if it's quadratic, that means one side has to be equal to 0 so that we could solve for x. So I'm going to bring everything over to the other side. So 9x squared minus 3x squared, negative 3x minus 3x, and 2 minus 5. And now you could try to factor this, or you could go to quadratic formula, or you can do a combo. I'm going to do a GCF of 3 first, just to make my numbers a little smaller. And then this, I can't factor it. There's no way. So I'm going to go on and do quadratic formula to solve for the two possible x values that will make f of g of x equal to g of f at x. So negative b, so positive 2, plus or minus b squared minus 4ac all over 2a. And when you clean this up, under the square root, you end up with the square root of 12. And the square root of 12 is the square root of 4 and the square root of 3. But the square root of 4 is 2. And then that gives us, when we clean up, if we divide all these coefficients or constants by 2, that's going to be 1 plus or minus root 3 over 2. And those are your two possible values for x. Okay, in the next example, you're given a few different functions, and right here, we're given some composite functions, and we need to determine which two functions here made up each of these. So what's the inside function, what's the outside function? So when I see p of x, the x plus 1 is m at x. M at x must be the inside function, and it was put into this square root function. So t at m at x, or t composite m. For the next one, the outside function is the cubic, the inside function is h of x. So cubic on the outside, the parabola on the inside. Or you could write it as a composite h. Finally, C, x squared plus 2x minus 1. There's nothing that looks quite like this. However, there does have to be something quadratic involved. So I'm thinking h of x needs to be involved somehow, and maybe this linear is being put into that x squared, and then when it's expanded, it matches. So we could give it a try. Let's see if it's h at m at x. So if it were, that would mean I'm replacing x squared with x plus 1 squared. So I'll write the bracket out twice, and then minus 2. If I do my distribution, x squared plus x plus 1 minus 2, this does in fact, if you collect your like terms, get x squared plus 2x minus 1. So h composite of m is the correct answer here. And final example, for each of these functions, we're going to determine the outside function and the inside function. So for the first one, the square root is the outside function and the inside is this x cubed plus 1. So for the next one, we have y equals the absolute value of the square root of x. The absolute value must be the outside function, and what's going inside of it is the square root. For the next one, y equals, again, absolute value of x squared minus x. The outside function is this absolute value. What's going inside? That little quadratic. Y equals sine of x plus pi. Well, the outside function must be sine x, and this angle x has been replaced with x plus pi. So x plus pi must be the inside. Next, we have 2 to the power of x minus 1. Well, the outside function must be the base exponential function. And what's going inside? Well, that exponent must be replaced with x minus 1. Because remember, your inside function is always replacing the x in the outside function. Next, we have x plus 1 squared plus 3 times x plus 1 minus 2. Well, it looks like x plus 1 is the inside function that's going into something. So first we have x plus 1 squared. So that must have been x squared. Then we have 3 times x plus 1. So that must have been 3 times x. And then minus 2. So that way these x's in the outside function are just being replaced with x plus 1, all squared. And finally, y equals x squared minus 10x plus 25. It may not look like there's an inside or outside function here, but if you were to factor this, so x times x to get x squared, negative 5 times negative 5 to get 25, you would say that these two expressions are equivalent. And when you write it like this, well, now it looks like the outside function is just the x squared, and the inside function is that x minus 5 inside the bracket. And that's it for your composite functions. You have functions within functions, which you can evaluate if you're given various equations or coordinates, or you can identify inside and outside functions, or you can be given inside and outside functions and you have to create composite functions. And for domain and range, you're just using your prerequisite knowledge of all of these functions and how their domain and ranges work. So that's it for composite functions.